Hello, everybody. I'm very pleased to be back here at the Italian C++ conference for the second year in a row. And I hope you will enjoy this talk on the topic of Extrema, correctly calculating min and max. As you know, the C++ standard library long ago picked operator less than as its ordering primitive. Now, in today's talk, I will explain why that operator must be used with considerable care, even in such simple algorithms as max and min. But I will also discuss the use of that operator in other order-related algorithms and show how easy it is to make mistakes when using that primitive directly. But let's begin with the intuitive approach. We define a pair of C-style macros, min and max, more or less like this. The two macros are almost identical, except we have swapped the arguments in one versus the other. Most of us in the C++ world prefer functions over macros, and so we write code which is more or less the same algorithm, but with slightly different syntax. And of course, so that we don't have to write a version of this for int and a version of this for unsigned and a version of this for double and float and char and string and my type and your type, we lift this and write it as function templates. This is C++20 style. However, those templates, reproduced here for your convenience, have just a few issues. For one, we have by value parameter passage, which is potentially expensive, for example, if you have large string arguments. Second, if the arguments have distinct types, it's not at all clear what the return type should be. And it's even not clear how I would do a generic comparison, even in a simple case like a signed versus an unsigned int. A simple less than just won't do the job. And of course, the major concern is always, are these algorithms correct for all values that are input? Now, these issues can be cured in a fairly straightforward way. We can certainly enforce type consistency just by naming the type of our parameters. And we can avoid expensive copies by using call by reference to const, but nonetheless call by reference instead of call by value. And after we make those adjustments, our min and max templates would look like this. Now, everything will have type T, so we have consistency. Both arguments will have the same type, and the return type will be the same. And we've switched to call by reference. However, none of the code that I have shown you so far is what I would consider correct. So let me show it to you one last time. I'll give you a few moments to see if you can spot what I consider to be the misbehavior. I'll be back in 10 seconds. Okay. Did you notice that each of these two algorithms returns B in the case that A and B are equal? Specifically, this is what I mean. This is troublesome because it does not seem reasonable to me that max and min of the same two arguments should ever give the same result. And by the way, someone noted online that it took Alex Stepanov 15 years to get these algorithms correct. So let's explore that a little bit further. In other words, the claim is that these algorithms do not properly handle the case of equal arguments. Now, I found somebody on Stack Overflow posted this saying at CppCon 2014, which was the first CppCon, Walter Brown mentioned that max returns the wrong value when both arguments have an equal value, and then concluded with the all-important question, why should that matter? Why should it matter which value is returned when the arguments are equal? Now, I have heard this question for many, many years in various forms, but more or less it looks like this. People say, look, equal values are equal, therefore they're not distinguishable, so it really should not matter which one you return, so this is an uninteresting case and really not worth discussing. However, it is my opinion that for min and max and related algorithms, these are superficial opinions and I believe are incorrect. And I believe Stepanov will agree. That's because there are many types where even equal values are distinguishable. Let me show you a very small example. Here is a very simple type named student. It consists of data members, one for the student's name, one for the student's ID, and a static data member I have named registrar, which in the constructor is the source of the ID component. The student's name is supplied when the constructor is invoked, but the ID comes from the registrar. And for the moment, the only other part of this type is an operator less than. And notice that we consider one student to be less than another only by inspecting their respective names. The ID plays no role, we say it is not salient, in deciding the order of two students. And of course, this should be called by reference and so forth, but I've simplified as much as I could for exposition. But the point is that since each student variable has a unique ID number, even if they compare equal, it does matter which one is going to be returned by min and max and similar algorithms. So it matters to consider the case of equal values. So here's what I consider to be the important insight. If we are given a pair of values, let's name them A and B, and we are handed them in that order, first A and then B, unless there is a reason to do otherwise, min should prefer to return A and max should prefer to return B. Never should they return the same value. I mean, it's intuitive, isn't it? If max returns one of the two values, min should return the other one. So when the values A and B are in order, min should return A while max should return B. And when the values A and B are out of order, min should return B and max should return A. And that's a key insight. We can say this even more succinctly, namely that we as programmers should prefer stable algorithms. Algorithmic stability is important, especially so because in cases like this, it costs us absolutely nothing to provide stability. What do we mean by that? Recall that stability is a property of an algorithm that is concerned with the order of certain items, and we say that that algorithm is stable if it keeps the original order of items that compare equal. In other words, a stable algorithm ensures that for all pairs of equal items, A and B, A will precede B in the output whenever A preceded B in the input. If an algorithm can guarantee that property, we describe that algorithm as stable. So because of this, here is what I recommend. For the min algorithm, I recommend the body look like this, that we return, well, is there a reason to do otherwise? Remember, we should prefer to return A from min, excuse me, unless there is a reason to do otherwise. So if there is a reason to do otherwise, namely A and B are out of order, then we'll return B. Otherwise, we prefer to return A. And I understand some people may prefer to code this as ask the question, are they in order? If so, return A, otherwise return B. But this is closer to the formulation that I prefer. There are times to use in order rather than out of order, but here I prefer out of order. Similarly, for max, as I'm sure you can predict, if there are reason to do otherwise, namely, if A and B are out of order, then we return A, otherwise we prefer to return B. Now, what does out of order look like? It's a very simple little function. You can certainly write this as a template. But given, I've changed the names here on purpose, given arguments here named parameters x and y, they are out of order whenever y is less than x. Which means they are in order, well, whenever they're not out of order. And I have been doing this for many years, and the code generation is typically not affected by using functions or function templates named in order or out of order, as opposed to using the raw less than. Now, I've chosen min and max as my exemplars for this topic, but the observations that I have made are by no means limited to min and max. For example, here is a merge algorithm written as a function template. And I know this can be coded differently and slightly more efficiently and so forth, but this is a very clean exposition. Please note for the moment that we are given a pair of ranges. B1 to E1 is the first range assumed to be sorted. B2 to E2 is the second range, also assumed to be sorted, both according to the primitive less than. And of course, we're given a destination of type out, here named 2. My claim is, just as in min and max, we should prefer to take from the first range by default, and we need a reason to take from the second range. And that's precisely how this has been coded in the highlighted if-else. If there is a reason, namely star B1 and star B2 are out of order, then notice I take from the second range, star B2. Otherwise, by default, namely they're not out of order, so I have no reason to do otherwise, I take from the first range using star B1. And this is just one example of what I've called analogous logic. Prefer stability wherever possible, especially when it costs absolutely nothing to provide it. Plus, it's a lot clearer. We know that we are looking for the order of two items, because we could be using less than for other purposes. But this makes it, in my opinion, crystal clear as to what is going on. Let's look at another example. Very small algorithm. Let's just sort two given values. So we are given values A and B by reference, not const, but reference. If they are out of order, then we swap them. And no matter whether we swap them or not, this function's post condition is that A and B are now in order. And again, for people who prefer to code asking whether they are in order, the equivalent code would look like this. If A and B are in order, we return because there's no work to be done. Otherwise, we fall through and swap A and B. It's more or less the same code with just one extra return. But we can go further. Instead of sorting two items, let's sort three. Please take a moment and have a look. This is C++20 code. So the if statements may look a little bit unusual, but this is valid C++20 code, not valid before. So we are given three items this time, A, B, and C, again by reference. If after sorting A and B, and I do that by calling the algorithm above, of course, if after sorting A and B, now we know because of the post condition that A and B are in order. If it turns out that B and C happen also to be in order, we can do an early return. This is a good use for an in-order predicate. Right? A and B are sorted by construction. If it turns out that B and C are in order, we're finished and we can return. On the other hand, if we didn't, then we know that B and C are out of order, so we'll swap those two. And because of the we know that B and C will be in order when we're done swapping. If at that point it so happens that A and B are also in order, again, we can have an early return. Otherwise, we need to swap A and B, and now we know that A, B, and C will be in order. This may not be a familiar presentation, but I suspect that every one of you knows this algorithm very well, although you may not have seen it in this form. Did you recognize plain old bubble sort? Because that's what this is. It's not a customary presentation, but this is bubble sort. Now, I went looking online to see how other people have coded this sort3 algorithm. And I found one that I'm going to show you on the next page, and then I just stopped looking. I found this on Stack Overflow. I had to elide a little bit of it in order to make this fit on the slide. But I think you'll agree that just by a glance, this looks much more involved, much more intricate, much more complicated than the algorithm I showed you on the previous page. And because of that added complexity, added nesting, multiple layers of ifs and else ifs and so forth, it's difficult to verify whether this is correct in all cases. But in my opinion, you only need to look right here. If A is less than B, then if B is less than C, we can return because clearly they're in order. That's true. That's not wrong per se, but I claim this algorithm does much more work than necessary because operator less than is not a substitute for a predicate based on in order, which is what this is trying to do. Just consider the case that A and B and C are equal. we would not be returning quickly. We would be doing some kind of swaps or half swaps for rotating. So this algorithm does strictly more work than necessary. Further, it's not stable. If I come in with A, B, and C all equal, then they're already in order, and I'm going out of my way to swap at least some of them. And now I've lost stability. Instead of doing no work, I've done work, and I've lost a potentially very important property. So again, consider in order and out of order whenever we're doing order-related algorithms. The main takeaway that I would ask you to keep in mind, there are two, they are complementary, that by itself, operator less than does not tell us whether its operands are strictly in order. It tells us something about their order, but it's not the same as in order. Not if you use the operands in the order that they were handed to us. What operator less than is good for is to tell us only whether, when we reverse the operands, whether they were presented to us out of order. I refer you again to my sample implementations of out of order and in order functions. So that's the main part of my talk. I have a little bit of extra time, so I'd like to talk about a bonus algorithm. We've talked about min and we've talked about max in isolation, but what about something called min-max? There are applications where one needs not one or the other, but both of the extreme values. And so there is a temptation to code a min-max algorithm like this. Given that we already have min and we already have max, let's reuse them, and we return a pair consisting of, first, the min element, and second, the max element. Now, I think we would agree that this is a correct implementation, but we can actually do better. And I suspect many or most of you have already figured out what we can do instead. It is, of course, cheaper if we can make a single call to, say, out of order than the two calls that we would make if we made separate calls to min and to max. And we can simply do this. Ask whether A and B are out of order, and if so, we return the pair consisting of B, comma, A. Otherwise, our default position is that we return the pair A, comma, B. And once again, we have stability at no extra cost. Stability is important in order-related algorithms, as we demonstrated earlier in this talk. And finally, because I suspect all of us at this conference, which, by the way, has been a very fine conference from my perspective, I'm very pleased to have been asked to present. Since we all like to code, let me leave you with a modest programming challenge in case some of you have not considered this algorithm in the past. The generalized min-max, where we have not only two values, but a range of values. So we are given a pair of forward iterators, which I've named from and up to. And let's assume that we use n to denote the distance from one to the other. Then what we want from this min-max is to return a pair of iterators I've here named little m and big M, which are iterators in the range that was given. such that m is the first iterator whose corresponding value is the smallest in this range, and capital M is the last iterator, not the first, but the last iterator in this range whose associated value is the largest. So small m and big M to give us the min, which has to be the first iterator with the smallest value, and capital M, big M, which has to be the last iterator whose associated value is largest. Now, this is not a particularly difficult challenge for anybody with any experience whatsoever to speak of. We can certainly do it by using as our primitive separate calls to min and max functions in an appropriate sequence. And if you do that, then you'll end up making very close to 2n calls to out of order, either directly or indirectly. But again, in case you are not familiar with this algorithm, there is a version of this algorithm which has been credited to Ira Pohl, which can give us a 25% performance improvement in number of calls to out of order. So if you've not seen it before, I recommend that you give this some thought, see if you can come up with it on your own. The key is in that coefficient 3/2. Instead of making two calls to out of order, two calls to out of order per value, because you have n values, right? We make 3 calls for every pair of values. That's where the 3/2 comes from. So that's as much of a clue as I'm going to leave you with in this talk. And with that, I thank you very much. It's been my pleasure. I did want to point out that this algorithm is in the algorithm header. It has the name min-max element. It is very slightly different in its interface, but very similar. So you can always look there for further inspiration if you wish. Thank you again. I will be happy to take questions and comment, but prefer to do so after the talk is finished. I'll come back to the tables in Remo and would be happy to talk with you then, answer any questions, and address any comments that you may have. Once again, thank you all very much. It's been my very great pleasure. And I leave you with a good morning, because here it is not yet 11 o'clock in the morning. Goodbye for now.